How's it going, everyone? Welcome. Julier Gonzalez here. Today we're gonna talk and explore about this new pattern for us, for me, but not new to the language or for the industry, known as CSP. And this is a model of how you can deal with concurrency. Now, because just to make a quick recap of how do we get here, as a way to understand that, especially if you are a UI specialist working with React, for example, or any other framework, front-end framework, at some point you will need to deal is with the concurrency in your application, aka that events that overlaps at a time. So in other words, events that come from the user. So for example, clicking, typing, scrolling, right? And all of these events, especially let's say for the clicking or for typing, okay? You want to, once you get these events, once you get these streams of data, you want to do something about it. Or if you're receiving data from the server, well, you want to do something with that data as it is. But as you can see, as a front-end developers, we receive data from the backend and from the user interface, right? So, because our task, our job is not only to build beautiful UI interface, so we need to understand the platforming in itself where we are building all of this user interface, which is the browser, right? And how that works and how that transform all of this characters, HTML, CSS, and JavaScript into pixel on the screen, and we need to understand is what is this particular pipeline, how this mechanism work, known as the critical rendering, the critical rendering path, all right? So once we know how this works, so now we take care of how can we build is this user interface, which is a good stuff, but also we need to deal with events that coming from the server. So how can we now deal with these streams of data, this series of data, or this series of streams that we're gonna handle in our application, right? So because of that, we are now looking at how can we deal with this concurrency, with this task that needs to be completed on the back end and on the front end at some point in the future. So because this is something that is quite complex and not exclusively for us as JavaScript developer, but we inherit a lot of this stuff from women and men across the history of computer science and software engineering. Thanks to all of that, shout out to them. So we are now on their shoulders. So and I say we, I include myself. So we are now is on their shoulders. So we are here thanks on there. So we are on top of the giant shoulders like them. Now, the idea here is to understand now what are the particular tools, aka patterns, that allow us to deal with this concurrency in our application. And for that, we need to explore what concurrency means, what is parallelism, what is the difference between concurrency and parallelism in a real life examples, and what are now the tools that allow us to deal with concurrency in our applications, such as callbacks, as well as it is trade-off. You know, we have callbacks, we have thunks, we have promise, and then we look at generators and iterators, and also is observables, and how can we deal with that, and now a specific library called RxJS to help us deal in those kind of scenarios when we need that kind of when we need to model our application in that way, we need to deal with this series of eventual values, and also is now the CSP. I am not aware of CSP. This is something that comes from Go, right? And then what I can say here is that each one of those tools or patterns that allow to deal with the concurrency, so for example, the callbacks, since the idea here is by passing now a control to a timer, all right? In other words, a platform's a functionality defined by the platform, in this case the browser or the server, if you're working with JavaScript at runtime. Now, this is something that allows you to use or defer task using the timer by passing now this set of instruction, aka a function, as a callback. Now at some point we hopefully assume now we have some sort of assumptions, but those assumptions are not entirely fulfilled. That's why we have now this inversion control. So for example, if you pass this set of instructions, you hopefully don't want to that be run too few times, too many times, too late, too early. Don't swallow up errors, preserve data context. So with callbacks, not only that, we also need to handle this time. So Thongs solve the problem of time by eliminating that as a concerning factor, and the way to do that is by now wrapping a function, async functions, with a function and passing everything that this function needs in a callback, that by the time that that data is there, you can now inside of this callback get that data out of that. Now this actually solves the time problems that we have with callbacks in our coordinations, but also is that we have now this inversion control. Promise kicks in and say, hey, I'm going to eliminate time as a concerning factor, wrapping around a value. So you can think of this as a callback manager, or aka an event promise, in other words, an event listener for future values. All right, that's what we now subscribe to the .then and the .catch, and by the time that that data is not there, or it is, we can now pass a callback here, and now the useful things of promise, unlike callback, is now promise give us now the sense of, so it provide now a flow control and a data flow. Okay, so this is huge, because with callbacks you have to do that by yourself, and this is also a problem that promise also have, which is the non-local, non-sequential reasoning about, which is something that Kyle Simpson he made this course to describe that particular problem, and that is because promise are not executing the way how our brain works or plans stuff, right? Pretty much like synchronous JavaScript. So anytime you define a statement, it'll be evaluating, and so on and so forth. So it won't go back to the previous one. It just evaluate all of that. Also, the functions, it's gonna run to completion. All right. So with generators and iterators, the value proposition of this is that allow us to describe is a syntactic form of describe is state machines. This is a fancy way to say we want to describe now is a series of flows from one state to another, to another, to another, to another, to another, and then descriptively list out the transaction. So how can we do this? And what is the value proposition of, or what is the reason of why we have, what do we have is generators? It's because it helps us here to describe this series of flows by getting so by resumes a pause the execution of this function, which is something that you can do with normal functions, because once you call that function, it runs to completion. But with generators, now we have this ability to get in and get out, get in and to get out in the flow, in the function flow execution. And this is huge, because with this resume and pause, pretty much like when you now, for example, want to look at YouTube video, all right, the Super Bowl, and then you want to make some popcorns and want to grab a beer close to you. So you pause that video, go back to the kitchen, do whatever you need to, grab that beer from the fridge, and you find out quickly some peanuts. So I'm gonna take this peanut with me in the beer, right? High calorie, that's right. High calorie intake while I'm not doing anything, just watching the Super Bowl. And now you hit here, enter, and finally you resume the video. So this is the analogy of the generators. It gives you the ability to now pause and resume the execution by yield a value or by accepting a value. So because these generators, when you invoke them, when you create that, now it gives you an iterator, which is a design pattern for typically stepping through data, such as, for example, when you want to query data in your database, anytime you get the first 10 values, and then you skip to the next one, skip to the next one, skip to the next one, this behavior is known as the iterator. But here, the thing is that we're going to step through a flow control. That's massive. That's massive. So whoever now control the iterator, control the flow of execution of that generator. So we also look at how can we recreate is the async and await with generators and iterators. And this is mind-blowing, because with this we can at least understand what's going on behind the scenes when we use async and await. All right. Now, this is great because now with generators it solves the problem of this non-local, non-sequential reasoning on your generator, because it allows you to describe now the series of flows and then you can define a long-running task by broken down and yielding periodically. This is something that now at the application level we need to handle that, and we are responsible for doing that. So why this is important, especially if you have now a function that at some point is now calling is an API, and then you get that data, and then with that data that you receive, you want to now send a new one, all right, to another endpoint, right? And you want to describe each one of those steps one line at a time, and because unlike with Promise that allows to describe much more this flow control or this error flow control, with generators is something that is quite cumbersome. So we look at ways of how can we do that in React, okay, by creating now a hook that allows us to now get the value out of here, okay, and now deal with the concurrency in an application. But in any case, so this is just to handle this single eventual value. But what happens when we need to deal with a series of eventual values, right? So now Promise is not helpful here. That's why we look at observables, which is another pattern in RxJS specifically, which is a library made by Microsoft. This is Mark Folks. So what observable say is that we need a way to model is get a single event source or get a single unit from an event source and then pass through a series of steps so we can distribute that in our system. Now, RxJS help us to do that. We also just briefly look at what this library is and how can we use, what are the concepts involved in RxJS, such as the observables and how you can create an observable, what an observable represent, which is the series of eventual value that you're going to emit, whether it's primitive or objects, and for that you use now of observable operator from the library. And if you want to create now a series of eventual values where each one of them is a promise or a generator or an iterator or an array-like style, you use now from. And when it comes to consume that, you just subscribe to that observable, right? And if you want to pass now this series of steps or transformation that you want to apply to each one of those elements that you're receiving, all right? Then we look at the common operators to do that. So for example, take, for example, take, skip, take until, skip until, pipe as a way to now provide all of this series of transformation that we want to pass through once we are generating our observables. Okay. Also, we can create is time-based observables. So, for example, time and interval. And a time is when I say, hey, I want you to now start from 0 and then emit this event after an X amount of time. With an interval, you say you're going to emit values here at this period of time. Also, we look at how can we work with map, all right, as a way to extract values and apply some transformation, filter, and the scan and reduce, which is are very helpful. Scan, reduce, and tab. Okay, tab help you for looking at these side effects, or for example, print console log to see what's going on in that string. Scan is for taking now that single value and then based on the previous accumulator apply a reduce function and give you that single value. All right, whereas in reduce it applies this reduce function and then once that observable is complete, all right, it's gonna give you the value. Also we look at how can we work with series of events or observables. How can we merge that? How can we now work with them, for example, with merge, concat, fork join, which is something that is not used but you can go with. And when you want to extract values of an observable, you can use the merge map and switch map as a way to discard everything that was before. I just want to focus on this one. Exhaust map. You say, hey, let me this thing pass through, and once it is complete, I'll go with the next one, right? In some other, this is known as the high order observables. And then how can we use that to construct is now, for example, counters. And looking at the most common observables, so for example, from events, no bindings, and the, how do you put it? No bindings, and what is the name? No bindings, and oh my god, no. From fetch. okay? And how you can actually use and how you can compose them in your application. So I will say that this is something that you must use carefully. It requires careful programming, this coordination. And right now, let's go to look at what this CSP means. So we can now actually focus on what we really care about. Oh, okay. Redux, that's right. Redux, can I? Okay. This is nothing. Goal, parallel, callbacks, exactly. And then we'll look at thumbs, and then we'll look at promise, and then we go further to generators and messaging. Messaging, that's right. And promise and observables. Here we are. RxJS. And finally, holy moly. Okay, RxJS. Okay. Yep. RxJS. That's right. And finally, to this one, which is CSP. Let me take a look at this. Oh, okay. Okay. Concurrency plus channel. Okay, this is CSP, concurrency plus channel. So concurrency plus channel. And the funny thing of this is that this particular pattern is something that is being used, for example, schedule notification. Okay, Android, if you're working with React Native application, you see that when it comes to do this in-app notifications, they use now a stuff known as channel, and this is something that is using behind the scenes. This concurrency way of doing it. What happened with all of this stuff that overlaps at a time and how they can deal with. Concurrency plus channel. Okay, concurrency plus channels. Here we are. There you go. Good.
Is, by the way, after I teach you this last pattern, there's a last exercise. So I'm going to teach you CSP in exercise 9. Exercise 10 is a much more sophisticated application.
Okay, so I'm going to write it this way.
Last pattern that I want to teach you is, by the way, after I teach you this last pattern, there's a last exercise. So I'm going to teach you CSP in exercise 9. Exercise 10 is a much more sophisticated application.
Okay, so now this one is this. Woo. You got it. Okay. So exercise 10 is a much more sophisticated app that Kyle Simpson, I think it is, like Kyle Simpson built. Called three. It's called a tale of three lists. Okay, it's called a tale of three lists. Okay.
And your exercise there is going to be to go back and revisit either reactive or CSP in the context of a much more sophisticated
Mm. So the idea here is to revisit all of these patterns in all of this pattern of a much more sophisticated application. All of this pattern in a much more sophisticated application.
So if you're looking for more practice on that stuff, it's coming with exercise. So don't feel like that's the last thing we're talking about. But I want to shift gears and focus on our last major pattern to introduce. It's called CSP.
Shift gear.
CSP is about modeling concurrency with channels.
Exactly.
We've modeled concurrency now 3 or 4 or 5 different ways. This is another way of modeling concurrency. And channels, if you want to think about what is a channel is kind of like a stream, it's kind of like a pipe, except there's one important characteristic, and that is the pipe has no buffer size, and therefore has automatically built into it this notion of back pressure. So if you've done stream-based programming before, you've probably heard or read about this notion of back pressure. But to illustrate that, I want you to imagine that I have 2 different ends of a hose.
Okay.
Another way of modeling, about modeling concurrency with channels.
So this is a
But I want to shift gears and focus on our last major pattern to introduce. It's called CSP. CSP is about modeling concurrency with channels.
This is about modeling concurrency with channels. Okay. So CSP is about modeling concurrency with channels.
We've modeled concurrency now 3 or 4 or 5 different ways. This is another way of modeling concurrency. And channels, if you want to think about what is a channel is kind of like a stream, it's kind of like a pipe.
Okay. So a channel is kind of like a stream, kind of like a pipe. Okay.
Except there's one important characteristic, and that is the pipe has no buffer size.
Okay. Except that the pipe doesn't have buffer size.
And therefore has automatically built into it this notion of back pressure.
And therefore they have this notion built in of back pressure.
So if you've done stream-based programming before, you've probably heard or read about this notion of back pressure.
So if you have done stream programming, you have heard about that.
But to illustrate that, I want you to imagine that I have 2 different ends of a hose, one way over here and then one way over here, and there's 2 people on either end, and they don't see each other, they don't have any communication between each other. And then this guy on this side says, I'm going to start pouring some water down through the hose, and the guy on the other end has the water coming out and spraying it. At some point, the guy who's spraying the water says, I don't want any more water. But he doesn't have a communication with this guy, so how is he going to tell this guy, I don't want any more water? Well, he's going to cap off the hose so that on the other end, no more water can go in because the hose is completely filled up. That's back pressure. That's a reverse way of communicating up from consumer to producer to say, stop producing because I don't want any more. Is everybody following me? This is like 50,000 foot view of stuff. Well, there are places in our application.
This is like 50,000
stop
foot.
Stop producing because I don't want any more. everybody following me? This is like 50,000 foot view.
50,000 foot view. 50,000 foot view. This is a very gringo stuff. 50,000 foot view. Oh crap. 50,000 foot views. Okay. Okay.
Well, there are places in our applications where we don't have a direct connection between producer and consumer because we've intentionally kept them separate. But we do want to have a signal, some way of signaling to the producer, I don't want to take any more data on this. Stop sending me stuff. In the RxJS world, that's their distinction between hot and cold observables. But converting between hot and cold observables is not quite as clean and easy, at least in my practice, as it might seem here. So another way of modeling that signal is to use a channel in a CSP system. Because a channel, as I said, is like a pipe that can only take one message at a time, and it automatically has back pressure. What that means is, you can't send me something until I'm ready to take it. And I can't take something until you're ready to send it. There's no queue there. It's one message that transfers through the channel. It's this notion of blocking channels. Now, CSP stands for Communicating Sequential Processes. This actually was a pattern invented way back in the 60s. A guy named Poor, he wrote this book called Communicating Sequential Processes. It was a model for managing concurrency. Some of you may have heard of the ACT system.
Who the fuck? Wait.
Blocking channels. Now, CSP, it stands for Communicating Sequential Processes.
Communicating sequential processes. Okay. So communicating sequential processes. It's a formal language for describing pattern of interaction in concurrent system. Formal language. Oh my god. Here we go. It's a formal language for describing patterns of interaction. Jesus. It's a formal language for describing patterns of interaction. There is a lot of abstraction here. Oh my god. Oh my French. There's a lot of abstractions. A formal language, okay, in logic consists of words whose letters are taken from an alphabet or a well form according to a specific set of rules and a formal grammar. Okay, so this formal language is now in linguistics and computer science. That's one of the reasons why linguistics and mathematics and computer science are here. It's like, what the French toast is this one? So a formal language consists of words whose letters are taken from an alphabet and well formed according to a specific set of rules called formal grammar. Right, so this formal language, which is a set of tokens or letters that are rearranged in a way that has meaning, okay? Exactly, in a way that has meaning to describe patterns of interactions. So all of this, what we're doing, even when I use the language, the English, to talk something, is just as a way to describe now recurring stuff, repetitive stuff that happened in our life, and then we want is to do something about it. And in our case, is this communicating sequential process is a formal language for describing interactions or for describing these patterns of interactions in concurrent system, in all of these tasks that overlaps at a time. Holy moly, bro. Oh shit. I get it why Closure and people from Closure actually now are using that. Tony Hoare. Oh my gosh, shout out to you. It's like, again, all of these people actually lay out the foundation as well as a secure e-commerce system. They lay out the foundation, including work to increase its range of practical applicability, increasing the scale of a system that can be tractable, analyzed. In all of this, is now a language. Oh my god. Shit. Is now a language. Is now a formal language to describe these patterns that occur. It's a formal language to describe patterns. Pattern of behaviors, because pattern of interactions, pattern of interactions in concurrent system. Okay. I know that I dive deep into this. Example is a vending machine, coin chuck and stop. Person coin stop, and then car stop. But again, it's just a way to describe that in concurrent system. God damn. Shit. Holy moly, bro. Oh my god. I get it. And not only that, wow, this is people that are sitting on the ivory tower. I get it, bro. A lot of people sitting on the ivory tower. I get it, bro. Yeah, of course. You are now, you still alive? Holy fuck. Oh my god, sir. Absolutely. Sir Tony Hoare. Oh shit. Is a British computer scientist who made foundational contribution to programming language, algorithm, operating systems, formal verification, and concurrent computing. His work earned him a Turing Award, usually regarded as the highest distinction in computer science. Of course, man. Because if you somehow find a way to deal with this concurrency in a mathematical way, oh my god. This is Jesus fucking Christ. Holy fuck. Nigga. Jesus. Jill Ping is a British computer scientist. Holy French toast. She's the daughter of the Lieutenant Colonel John Ping and Dinah Good. Holy crap. You know what? These kind of people actually live very steady, chill life. You know? Very steady, chill life. Turing Award in 1980. Jesus, French, those guys. What the? No, chill. Hoare's developing a sorting algorithm. Oh my god, the sorting algorithm. Quick sort. He developed Hoare logic and axiomatic basis for verifying program correctness. In the semantic of concurrency, he introduced the formal language communicating sequential processes to specify the interaction of concurrent processes, and along with H's distract, formulated the Dynamics philosopher problem. Since 1977, he has held a position of University of Oxford and Microsoft Research in Cambridge. And of course, I get it. Similar to him, Sir Tony Hoare, okay, and Grady Butch, the Butch methods, exactly, Grady Butch, holy moly, bro. Holy moly. This is the kind of people when you say, "Oh, you were young." You were young? Of course, man. Duh. Esa guayaberas, that Hawaiian shirt, t-shirt. Okay. That's interesting. Holy moly, bro. Oh my god. At IBM. Holy fuck. It's rising one level of abstraction. With Grady Butch. Okay. Again, I get lost here. No, but come back. Ooh, come on, Grady Butch. Okay. Yep, Grady Butch. Here we are. Chief scientist at IBM. Holy moly. Holy moly, bro. Sirton Hoare. I don't know how you pronounce that. Hoare, that kind of stuff. Of programming. Yep. Holy moly. Okay. Jesus fucking. You know what? All of it. And to me, it's quite interesting. We want to reinvent the wheel, but this is silly. At least if you're not if you're not part of the elite of that industry. If you're not, you just only need to learn all of this concept and know what is the use case of all of this. So, okay, Jesus. So, Tony Hoare. How Jesus? I want to know how you can pronunciate that. Translator, translator, right? Help me here, translator. No, okay. Translator, English to, yeah, to English, bro. Style English. Oh, I think.
Tony Hoare. Hoare. Hoare.
Okay. The context. But yeah, Sir Tony Hoare, he developed this. So Tony Hoare developed this. Was the first describe by Tony Hoare in a 1970 article, and has since evolved substantially. CSP has been practically applied in industry as a tool for specifying and verify the concurring aspect of a variety of different systems, such as T91000 transputer. Oh, intent for transputer. Jesus. Transputer. Transputer were intended to be programmed using the programming language OCaml based on the communication sequence process calculus. The transputer was built to run OCaml, specifically more than contemporary sys design were built to run language like Pascal or C. OCaml support concurrency in channel-based inter-process or inter-processor communication. Question: are they still available in the market? they are still available in the market. Adoption. And built as IBM Blue Gene are real world incarnation of Transputer Dream. Microelectronic design and innovation. One of the most recent commercial development has emerged from the firm Exmos, which has developed a family of embedded multi-core, multi-threads processor which resonate strongly with the Transputer and Enos. There is an emerging class of multi-core, many-core processors taking the approach of network on a chip, such as Cell Process Adapta. Interesting. Private equity. Why not surprised? Okay. This can be useful. This can be useful. Oh. Funding from Amadeus Capital, DFT Spirit, and Foundation Capital. It also has a strategic investor, Robert Bosch Venture Capital. Oh crap. And Huawei Technology and Synlink, which in 2014 invested 26.2 million. Additionally, they receive an investment through the sales of 22.3 of the company's shares and Perlut Trust, blah 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 blah. In July 2017, Exmo acquired Steamis, a company that specializes in auto algorithm for source separation. In 2019, Exmos raised 19 million in funding from Harvard, European Growth Capital, and existing investor. And in December 2023, Exmos signed a joint development agreement with Sonical for Headphone 3.0 technology. AI IoT, artificial intelligence of things. Holy crap. In 2018, KPMG published a foresight study of the future of AI, including scenarios until 2040. The analyst describes scenarios in detail where our community of things will see each device also containing its own AI that could link autonomously to another AI together, perform tasks intelligently. Value creation will be controlled and executed in real time using swarm intelligence. Many industries will be transformed with the application of swarm intelligence, including automotive, cloud, medical, military, research, and technology. Oh crap. No crap. Okay. Ooh, we get into the okay. A transputer. Okay. CPU and the other is transputer. Alright. It's a series of pioneer microprocessors from the 1980s intended for parallel computing. Exactly. Because at the end of the day, we are working with CPU, right? This computer process unit, general purpose, right? But now these are very specific for this. What is the main use case? I would like to, oh my god, transputer. What is the main industries and use cases of a transputer? Military, I think it's military. Parallel computing research. Transputers were designed specifically for parallel processing with built-in communication link that made it easy to connect multiple processors together. university and research labs use them extensively to explore parallel computing concepts, industrial control and automation. Their ability to handle real-time processing and parallel tasks made them suitable for controlling manufacturing equipment and industrial processes, graphical and image processing, scientific computer and signal processing. Their architecture made them effective for digital signal processing. Digital signal processing, the most in telecommunication and audio processing. Since this was a relatively niche and historically significant technology from several decades ago, while I aim to be accurate, some of this specific application may be subject to hallucination and should be verified against other sources. You're a good generator of bullshit. Oh crap. Okay. But transputer exists according to Wikipedia. So okay, good. Transputer exists. Okay. Transputer exists. Deal with it. Oh crap. Okay. So we look at this. Communicating sequential processes. And it is a formal language for describing patterns of interacting with concurring system. How are you going to interact? Oh my God. How are you going to interact with concurring system? In other words, you can think of this like how are you going to interact with men and women in a, for example, social events, or in a gym, or in your daily life. You know, how are you going to interact with them? Or during a party, all right? It's okay. It's a formal language. Jesus. Okay, it's a formal language. It's a formal language for describe, or it's a formal language exactly for describing patterns of interaction in concurring systems. Okay, Jesus French toast guy, bro. Okay. So it is CSP, specifically CSP is a formal language for describing patterns of interacting with concurrent systems. Holy French those guys. With concurring system, or of interacting in concurring system, systems. Okay, concurrent system, like how you gonna deal with this string of events such as typing, the user typing or clicking. He's raging on that click, so you're gonna wait. So let's assume that the user is raging on that click. You say, okay, chill, I'm gonna handle this when you are ready, when you're calm, right? And receiving all of this stream of data, click events, and then when you're chill, you're gonna do that. And this is what the difference between is the throw and the bounce. The bounce says, hey, I get that. So once you're done firing up all of that events, and you chill a little bit, then I'm gonna do what it needs to do. And the other is now throw. Throw say, I'm gonna let this pass through, no matter how many times you're clicking, and then after the next amount of time, I'm gonna let this pass through. This is another one. Okay, CSP is a formal language for describing pattern of interacting in concurrent system. Okay. So based on what Kyle Simpson mentioned, CSP is about modeling concurrency with channels. Mhm. Is a member of the family of mathematical theory of concurrency. Oh my God, mathematical theory of concurrency, known as process, known as process algebra or process calculi, based on message passing via channels. But it's interesting because it's using now algebra, these generalizations of process calculi, process calculus. Oh, crap. Oh my God. Mathematics of processes, parallel composition, communication, sequential. Oh, crap. This is a mathematic, bro. This is a branch of mathematics, a thing that you, stuff that you can learn. The mathema. Which, from mathema, mathematics. Or mathema is what one gets to know, lo que uno llega a aprender in Spanish. Okay. Jesus. All right. CSP is one of them, and then you have now CSS, ACP, and Lotus. That's interesting, and this is also something that now it is on extreme demand of all of this fintech, right? All these fintech applications, now they have to deal with these large volumes of concurrency or large volume of stuff that needs to happen and overlaps at a time. Jesus, man. And not only that, it's also aims to the AI as well. Aiming to the AI. Holy moly. All right. Okay. Based on message passaging via channels. But again, CSP is about modeling concurrency with channels. But this is a formal language. For describing patterns. For describing patterns. This is a formal language for describing patterns in concurring channels. No, it's not like that. It's a formal language for describing pattern of It's a formal language for describing patterns of interacting with concurring system. So, an analogy of this: imagine that current system is a person, okay, it's a woman or a man, okay, and you want to now is describe how you're going to interact and what is the pattern that you're going to interact for men and women. Holy moly, bro. And automate that process. Okay, and all of this is just to have control of this. Make no mistake about it.
One message that transfers to the channel. Quite simple. Practice. So another way of modeling that signal is to use a channel in a CSP system. Because a channel, as I said, is like a pipe that can only take one message at a time, and it automatically has back pressure. And what that means is, you can't send me something until I'm ready to take it. And I can't take something until you're ready to send it. Everybody follow me? There's no queue there. It's one message that transfers through the channel. It's this notion of blocking channels.
One message transfers through the channel.
There's no queue there. It's one message that transfers through.
Okay. there is no queue there. One message transfer to the channel.
It's this notion of blocking channels. Now, CSP, it stands for Communicating Sequential Processes. This actually was a pattern invented way back in the 60s. A guy named Tor, he wrote this book called Communicating Sequential Processes.
Exactly. So Tor exactly, this pattern was described by Tony Hoare in the 60s. In the 70s. All right.
It was a model for managing concurrency. Some of you may have heard of the actor model of concurrency, and there's a close but not direct relationship between the two. The major difference with actors, at least from my research, the major difference with actors versus this thing I'm about to talk about. With actors, when you send a message, it's asynchronous. You send it.
Okay. So you have now the actor based model. The actor model. In a computer science, a mathematical model of concurrent computation. Now we get into the. Now, oh my God, this is the big leagues, bro. Big boys, big girls. Oh crap. Okay, where am I getting to? Where am I getting to? Influence. And practical software development. Address issues, scalability, the challenge of scaling up concurrency both locally and non-locally, transparency, and inconsistency. The actor model address issues in computer communications architecture, concurrent computer programming language, and web service include the following: stability, transparency, and inconsistency. Multi-agent systems. This particular patterns is for them. Design systems. Oh crap. What is the actor model and when to use it? Oh, that's interesting. When order really matters. In the actor pattern. If one of the actors fails, when dealing with synchronous problem, Mhm. From their blog. The actor model. Mhm. Okay. But you mentioned something here. Was described.
The message, the difference with actors versus this thing that I'm about to talk about. With actors, when to the names. Some of you may have heard of the actor model.
Mm-hmm. So type of modeling concurrency. Because I think this is quite important here. You have now the actor, okay, actor model, and you have now the CSP.
Of concurrency, and there's a close but not direct relationship between the two. The major difference with actors, at least from my research, the major difference with actors versus this thing that I'm about to talk about. With actors, when you send a message, it's asynchronous.
Mm-hmm. So according to Kyle Simpson, the difference between the actor model versus CSP is that actor model, when you send message,
My research, the major difference with actors versus this thing that I'm about to talk about. With actors, when you send a message, it's asynchronous.
okay, actor models, because both of them work with channel. Actor models send message asynchronously.
You send a message, and at some other point, somebody on the other end picks it up. With CSP, when you send a message, it's very synchronous.
Okay. CSP, when you send a message, is synchronous.
At least the semantics are. It's very synchronous.
Exactly. The semantics. But the way to describe that. The semantics.
When I want to send a message, there has to be somebody on the other end that's ready to take it. Because my host can only accept one message at a time. Okay? That's the major difference. If you've heard about actors, it's the major difference between synchronous message passing with CSP versus asynchronous message passing. So communicating sequential processes. What is this all about? It's about modeling your application with lots of tiny independent pieces that we call processes. And what is this all about? It's about modeling your application message passing with CSP versus asynchronous message passing. So communicating sequential processes. What is this all about?
Okay. What is this all about? Okay. I'm quite redundant here. What is this all about?
It's about modeling your application with lots of tiny independent pieces that we call processes.
It's about modeling your application with a lot of tiny little pieces that we call them processes.
And if JavaScript had full like threading to it, we could do like you can in Node where you can set up child processes and stuff. If we had like full threading, then every independent piece would be on its own. like threading to it, if we could do like you can in Node, we can set up child processes and stuff. If we had like full threading, then every independent piece would be on its own thread, and it would be running entirely independently of everybody else. Well, that's great because a lot of the times they are doing their own thing, but there are cases where these two independent pieces need to coordinate with each other. So you have two different parts of your application that are normally just kind of running, doing their own thing, but there is a state in which they get to where they say, I need to communicate with this guy, and this guy gets to a state where he says, I need some information from that guy. So whatever they've been doing independently, they get to a point where they say, we need to coordinate and send a message in either direction, or perhaps about one message this way and this way. And then as soon as the messages have passed,
so in JavaScript, if we have, okay,
they say, I need to communicate this independently of everybody. You can and Node, we can say. And if JavaScript had full like threading to it, if we could do like you can in Node, we can set up child processes and stuff. If we had like full threading, then every independent piece would be on its own thread, and it would be running entirely independent.
Exactly. So in JavaScript, we can have each independent piece running in their own thread. Okay. But at some point, exactly. So you can have each independent piece running in their own thread. Okay. Doing all this kind of stuff.
Well, that's great because a lot of the times they are doing their own thing, but they're
and that's great. Exactly, and that's great because a lot of the time they are doing their own thing. But at some point, some of these pieces needs to communicate with each other, and that's when we need to some sort of coordination.
There are cases where these two independent pieces
Absolutely.
coordinate with each other. So you have two different parts of your application that are normally just kind of running, doing their own thing, but there is a state in which they get to where they say, I need to communicate with this guy, and this guy gets to a state where he says, I need some information from that guy. So whatever they've been doing independently, they get to a point where they say, we need to coordinate and send a message in either direction, or perhaps about one message this way and this way. And then as soon as the messages have passed, they become unblocked and they go back to being independent. That's what we mean by processes, is that these things could
And by the time they pass their messages, they unblock and continue to do their thing.
Theory run independently. Now, we know within JavaScript, things aren't actually running independently like that. But we have seen something today that does sort of act like that.
It's like generators. But so we know that in JavaScript, you know what? No, I need to use you know what? But we know that in JavaScript, okay, we know that in JavaScript, we don't have threads. We don't have. So, but we know in JavaScript, we don't have this. We know that in JavaScript we don't have this multi. We don't have this threads. So everything is joined together. Joined together. However, but what we have seen so far
independently. But we have seen something today.
exactly. But we have seen something that mimic that behavior.
It does sort of act like that. Does anybody know what I'm talking about?
The generators.
Then we see something today that sort of acts like it can just block itself and not affect any of the rest of the application. Generators, right? So what if I had a bunch of different generators that were all running in different places and they were running independently with each other? And then at some point, two generators said, hey, we need to coordinate with each other. So let's have a communication channel where we can both block each other, both block waiting for the other one to show up. And as soon as both of us have showed up, we can send a message back and then we can go back to doing it.
Exactly. So the idea here is that the idea is to have a bunch of generators in when they need to exactly. So the idea is to have a bunch of generators. This is a small piece of code, and when they need to communicate, they block each other and pass their message. Okay, so the idea is to have a bunch of generators, and when they need to communicate, they block each other and pass their message. So then continue to run and unblock them. So and then unblocks them and continue to run. Which technique we have so far?
Basis for CSP. And while that sounds fantastically more complicated, it is. It's also fantastically more powerful because we can literally model every independent piece of our application totally separate of everything else. And all we have to think about is when I need a message, I wait for the message. Or when I need to send a message, I wait for the sending of the message. And other than that, we have no understanding or knowledge whatsoever of any of the other pieces of the system. So theoretically, the implementation can take each one of those little processes and put them on an entirely separate thread, and the application will still work exactly the same. This model for concurrency, the CSP model for concurrency, is so powerful. It is the model for concurrency in the Go programming language. It's also what closure and closure scripting is. So it's not just me making something up and saying it's cool. Some really, really, really super smart people have said this is the way to do concurrency. And in Go, they do have threads. So every Go, it's called a Go routine. Every Go routine does end up spinning up on its own entirely independent thread. It's one of the magic reasons why Go has so much efficiency, so much performance to it, because I'm able to spin up all these different pieces of my application in separate threads, but I have a really simple way of communicating between the two through blocking channels. So let me try to illustrate in code what that looks like. Make a channel like I do up here on line 1, and then I have this process 1, which is a generator, because we're expressing this.
CSP. All right. This library can help you when you want to remember some weird formatting rules of CSP and want to avoid typos. Okay. and send receiver channel. It's only selecting over a set of receiver, and even there it doesn't offer something like the default clause of Go select statement. Go routines over OS threads as the unit concurrency. Okay. This is getting too much into the weeds. No. No.
Terms of JavaScript. He wants to send something down the channel, so he uses a method called put. And he says, this is the channel I want to send it on, so we pass channel as the first, and then we pass the next argument as a message that we want to send. You notice I'm using yield in front of put because I want for the process one generator to pause until somebody on the other end of that channel says, I'm ready to take that message. So I say yield put, which locally blocks the process one until somebody else comes along and unblocks it.
Is that to locally block the process one?
Process in my application, maybe in an entirely different part of the app. He's running along and he says, I need a message from the CH chain. So he says, I'm going to yield on a take, like I'm doing with line 10. It does not matter who gets there first. That's what's cool about it. I don't have to worry about whether or not there's a message waiting for me or not. I just say, I want to take a message and I'll wait until one's ready. Maybe it's ready right now, great. If it's not, I'll just patiently wait. I want to push a message down. I don't have to know whether or not somebody's ready to get it or not. I'm just going to wait until somebody's ready to take my message. That's what lets them be so independent. Because the semantics of this communication channel take care of that communication, that back pressure for it. So whenever process gets to line 10 and it says I'm ready to take it, immediately that message transfers through the channel and process 2 is unblocked and process 1 is unblocked, and then they just go on about their day. And then we get to line 5 and we say, wait a minute, I need a message from the channel, so I'm going to wait again. And then process 2, he's running along and he says, hey, I've got a message to send on the channel, so I'm going to wait until somebody's ready to get it. And he sends a message back up the channel. And then process 1 is unblocked, and then process 2 is unblocked, and they go on about their day. So you can have hundreds of lines of totally independent code that doesn't have to worry about any other piece of the system. And the only part that has to worry about it is when you know, I've got a channel that I need some data on, or I've got a channel that I need to push some data on. I'm just going to wait for somebody to tell me that's it. And underneath the covers, this abstraction, the CSP paradigm, is what manages all that complexity. Now, really, really smart folks in Go and ClojureScript, they're pretty convinced this is the most powerful model invented to date for concurrency. And I'm not one to bet against them. I think they're right. I do think this is the most powerful pattern that I've ever seen or heard anybody talk about for concurrency. I'm fascinated by it. I've spent the last year researching how to understand this deeper and see practical ways of applying it to my user interfaces. And I spent a year at it and I still feel like I'm barely scratching the surface compared to these smart people. And, you know, that whole like standing on the shoulders of giants, I'm like clinging on for dear life. I don't even hardly know the stuff that they're doing. But I'm convinced that there is a whole lot here that we haven't even really uncovered and scratched the surface. So ClojureScript, guys that maintain ClojureScript, specifically a guy named David Nolan, who goes with Swanadot on Twitter. Super brilliant guy. Every time I hear him talk, I'm just like, how did I even like? He just drops down this knowledge like it's so easy and learning so much. But he's got a UI framework called OM, and it's ClojureScript. ClojureScript is ported, it's Java. ClojureScript is Clojure that can run in JavaScript in the browser. And it uses CSP all over the place. It models the entire user interface in CSP. He produces the most amazing and most performant user interface that I've ever seen. So I'm convinced that there's a whole lot of we haven't scratched the surface of the capabilities of it. That's why I'm trying to convince people to think about this as well. This is another one of those tools to start to model our applications. That's a pretty simple example. How might we have a slightly more complex one? This one, I've got CSP in front of everything because I'm now using a library. There are libraries for CSP, and one of them uses the namespace CSP for it. And you notice that we call it .go because we're modeled off of that Go routine mentality, the stuff that comes from the Go language.
The Go routine,
this is
okay.
how I actually pass those two generators to something that we do it. The previous code snippet just pretended that somebody did it. This is a little bit further step along, shows us how it would work. We would pass those generators in to a method called Go. And you notice now I have a while true loop going, which is going to let those things run forever. That's how you end up modeling these independent processes that run your application, is you end up basically having every one of them with a while true loop, and they're all running independently. So here I've got, on line 1 through 5, I'm declaring a Go routine that's going to, every time somebody lets it, it's going to generate a new random number and push it down the channel. It would like to do that as fast as possible. But if you'll notice, the notion of this blocking channel is it's going to be, there's a back pressure here. It's not going to be allowed to push anything down the channel at any faster speed than somebody on the other end is consuming. You see that? So on the other end of the channel, I have another Go routine in an entirely different part of my application, and he's waiting every 500 milliseconds, and he's pulling something off the channel once every 500 milliseconds. Does that sound familiar? Does that sound like a sample? 500 milliseconds. You see that? So on the other end of the channel, I have another Go routine in an entirely different part of my application, and he's waiting every 500 milliseconds, and he's pulling something off the channel once every 500 milliseconds. Does that sound familiar? Does that sound like a sampled stream? This is a way of modeling the sampled stream through CSP semantics. So the guy up on line 3 is not able to push the random values any faster than somebody's consuming, and the guy down on line 9 is consuming them only once every 500 milliseconds. The guy on line 9 has no idea how those values are being produced or where they're coming from. The guy on line 3 has no idea who's taking them. They're literally completely independent sequential processes. But they're able to coordinate through blocking channel semantics. Yes?
Sure. Walking through this just a little bit more, you might be doing it now, but there's the two takes, right? Yield on line.
The first one on line 9, yep.
Line 9. That is taking a value from the first one.
But look where it's taking it from, because take always requires a channel. And what we're passing to it is a channel that is created by the timeout function. So the timeout utility, which is provided by this library, creates a channel that won't push a message down until after 500 milliseconds. So we're basically saying I want to take from that channel, and I'm going to wait until that channel gives me something. That's a way for us to do the blocking. Blocking the local.
Maybe I missed what is the channel. So
the first argument to the put and the take methods that we're showing here is always the channel. So if I take from a channel produced by the timeout method, it doesn't matter to me what channel it is, but I know that that channel is not going to send me a message until after 500 milliseconds.
Oh, okay.
Yeah, it's kind of like in the previous slide. We made one. These libraries have different ways of making their channels, so that's how you make a channel. It's like a one. Here, that channel we just know it exists.
So channel is kind of a global, though. You say they don't know about each other, but somehow you have to have this global state that's.
That's, in my opinion, one of the downsides of this particular library. It assumes global variables. You'll see that other libraries like mine don't do that. Okay? But yes, that's a detail that you have to figure out some way to transport the channel so that the two. The only thing they have to know about is they have to share a reference to the channel. There's lots of different ways that we can do that. Global variables are just one. Okay. Last thing I want to show you is the puts and takes are pretty straightforward. But there are actually dozens of different primitives that are defined here.
All right. Okay. That'll be all for this video. Take care. Bye-bye.